Hey everyone. So a couple of students were asking me to go through the information found here in assignment 7. And this has to do with the radical halogenation portion, which is the second part of the assignment. And so I do understand that this is a little bit more difficult, and so having a little video walkthrough might be useful, and that's exactly what we're going to do here. So for this question, it states that this is a radical bromination that forms an unexpected product, because somehow it results in a bromine on a tertiary carbon that did not begin with a hydrogen. Right? Notice how in our starting material, the carbon highlighted in pink already has 4 bonds to it. In the product, if we highlight the exact same carbon in pink, that is where the bromine ends up. The other thing that you might notice is that in the starting material, one of the bonds to that carbon is this double bond that sits right here. Notice that in the product, that double bond no longer exists between those two carbons. Instead, it's moved over to where I'm highlighting now in green. Right? It's between these two carbons here. So sometime during this mechanism, we see that this reaction is moving that alkene. And to give you a little bit of a hint on this, I did state that the reaction has an interesting resonance form that stabilizes the radical. And so the first thing we need to do is we need to determine where on this structure are we going to be pulling a hydrogen, because either way that we look at this, a radical halogenation has to have a hydrogen that's being abstracted from the molecule in order for us to actually form the product. So that's the first thing we have to ask ourselves. Where is the hydrogen coming from? It's clearly not coming from the carbon with the bromine, but the other carbons of interest are the ones that we have highlighted over here. But notice that even in these carbons we have highlighted, if I were to highlight this one in red, you would say that in both structures it still has 4 bonds. However, this carbon over here that I can highlight in blue, you'll notice is not the same. Here in the starting material, it only has 2 hydrogens, right, as well as the 2 carbon bonds. And then over here, we lose one of those hydrogens, right? Notice that we go from the 2 over here to just 1. So clearly, whenever we're talking about this as a radical halogenation, the hydrogen that we're losing must be one off of this carbon. The question is, does this make sense? Well, if we think about this in terms of the radical that would form from this hydrogen being taken, we would have a radical right here. And that radical is 1 carbon away from a double bond, which means that we can draw a reasonable resonance form here that utilizes the radical in such a way that we get to place it onto that tertiary carbon where our bromine ends up. Right? And so this is a telltale sign that that resonance form is very important for us. So what we're going to do is we're now going to draw this mechanism for the radical bromination, keeping in mind that this hydrogen is the one that we want to take. All right, so let's go ahead and let's just erase that, and we'll start off with our first step, which of course is initiation. In our initiation step, this is always where our bromine-bromine bond is going to be broken, right? Light comes in, we break the bromine-bromine bond, and 1 electron ends up being given to each bromine, which gives us 2 bromine radicals. Right? And so these bromine radicals are what we're going to use in our propagation 1. Now, our propagation 1, what we're going to end up seeing is that hydrogen that we were talking about beforehand on that carbon that we have highlighted in blue up top, that is the one that we actually care about. All right, so we're just going to draw this out with that hydrogen shown, because our bromine radical is going to be the thing that comes in and actually interacts with this hydrogen. Right, we're going to form the bromine-hydrogen bond using 1 electron from the bromine and 1 from the CH bond. We're breaking that CH bond, and we're giving 1 electron to the carbon itself. And so what this gives us is a radical on this carbon right here. And of course, this is where we see the importance of that resonance form. Keep in mind we've also made HBr. This is going to be important in a little bit for our calculations. So before moving on, we should show this resonance form to get a little bit more of an idea on what's happening here. Well, whenever we look at this structure, we can draw out that exact same resonance form that we had drawn before, right? Where we use 1 electron from the radical and 1 electron from the double bond to make a new double bond. And then we use the other electron from the double bond to form a new radical, right? So this will essentially give us a new structure where we have this double bond right here, and we have the radical on this carbon. Now, whenever we're looking at radicals on carbons, and we think about how they're going to be affected based on the actual structure, we can say that the more stable radical is the one that this is going to go through in terms of the mechanism. So looking at these two structures, the reason this resonance is so good is because this first structure is a secondary resonance stabilized carbocation. And then the bottom one, if we take a look at what kind of carbon that radical is on, this is a tertiary resonance stabilized radical. So since this structure is so much more stable, we would say that this is the primary structure that's going to be undergoing the rest of the mechanism. So this is what we're going to see go through in propagation 2. Right, propagation 2, we're going to utilize that exact radical interacting with another molecule of Br2. Right, and that radical is going to use the one electron to form a bond with one of the bromines. The bromine-bromine bond will break using one electron from the bromine and then giving the other to the other bromine that's there. And this, of course, gives us the carbon-bromine bond being formed, as well as a new bromine radical that can go back into propagation 1. Then we have to end it all with termination. And so termination is going to be where two of our radical species come together, and as I said beforehand, it's typically going to be the radicals that form the products. So our bromine radical and our carbon radical can come together to form a CBr bond, and that of course makes our product. So now with all this in mind, we can move on to the next step, which is we're looking at the bond association energies for each step, and we're calculating the enthalpy of each and then the overall enthalpy of reaction. Now, I've already done this here on this slide for us because I don't want to hop back and forth between our bond association energy table, but all these values come from the bond association energy table. And the only thing that you have to keep in mind is in each of these steps, what is happening that is giving us some level of energy. And so in this first one, the only thing that's happening is the bromine-bromine bond is being broken. Right? It is splitting up to make those two bromine radicals. So when we calculate our enthalpy of reaction, we are essentially going to be utilizing the idea that delta H is equal to bonds broken minus bonds formed. Right, so in our first step, since we're breaking the bromine-bromine bond, as we had shown, that's going to be 46 kilocalories per mole based on the bond association energy. This, of course, will give us a positive delta H because that is a bond broken. Notice that bonds formed end up making our delta H more negative because they go over here and they are subtracted from our overall term. So let's take a look at what propagation has for us. We don't include propagation 2 towards our energy, nor do we include the resonance, right? Because we already actually account for that a little bit based on our bond energies. When we look at propagation 1, we have two different things happening. We have a carbon-hydrogen bond being broken, and we have the hydrogen-bromine bond being formed. And we have to show both of these in terms of our propagation step. The broken bond in this case is a CH allylic. If you look in the bond association energy table, you would find that the idea of allylic comes from the fact that anytime you have a double bond and it is within resonance with something like a radical, this position would be considered allylic. The same thing that we can say about this is our bond formed, which is our HBr bond. And so this time we have two different values and they are contrasting one another. We have a broken bond at 87 kilocalories per mole, and we have the formed bond at 88 kilocalories per mole. So if we just subtract those two, because remember that we are taking our broken minus our formed, so we're essentially just doing this math right here, 87 minus 88, we find that this comes out to be negative 1 kilocalories per mole. We can do the same thing in termination. In termination, what we see is that we form this carbon-bromine bond. The best bond association energy we can come up with for that is that we formed a tertiary carbon-bromine bond. And so this gives us a bond association energy of 65 kilocalories per mole, and the delta H of this step, since this is a formed bond, is going to be negative because our bonds broken is going to be 0, our bonds formed will be 65. So this comes out to be negative 65 kilocalories per mole. Now if we take all of these values and add them up, that's where we come up with the delta H of reaction at negative 20 kilocalories per mole, right? And this is going to be a useful value for us because now we're going to look at this in terms of an energy diagram. So we can use the energies that we calculated in question 2 to draw an energy diagram that shows the energies of each intermediate and their relative energies in comparison to one another. How do we do this though? Well, the easiest way is if we take a look back at each of these steps. There's a reason I made you calculate step by step. It's because we can utilize each of these delta H's to give us an overall change, right? Take for example our initiation step. Now notice that after initiation, we have gone up 46 kilocalories per mole in terms of energy. In addition, we're forming intermediates when we do so, because notice that after our first step is done, we've broken that bond, and now we have what is labeled in pink here as I1. Now also notice that whenever we call this I1, we also relate this back to the next step where the carbon radical or the carbon hydrogen bond that's still present is also considered to be part of I1. These are considered intermediates because both share the bromine radical, right? This is a shared species. And that's the thing that's actually giving us the high energy. So let's go down here and let's take a look at this. Well, since we're told that this is a positive 46 kilocalorie per mole difference, we can say from our reactant, we are going to go up 46 kilocalories per mole, right? Because that's what we were saying, plus 46. So how can we draw that? Well, first we can throw in our intermediate right here. And as a reminder, when we're looking at these energy diagrams, it's not based on an exact measurement. We're just drawing them in relation to one another. So we can draw this coming up, and there we go. We have our I1 here. And as a reminder, how we came to this conclusion, and we'll keep this dotted line here for later because it'll help us out a little bit, is we essentially said that the distance between our reactant energy and I1's energy, this was our delta H of initiation, right? That 46, positive 46, kilocalories per mole. Now we can do the same thing for I2, but notice after propagation 1, where we're forming our HBr bond and breaking that CH allylic, we actually get paid back a little bit. We have a negative 1 kilocalorie per mole delta H here. So that means that we're going down in energy. Now, it's not much energy that we're going down, it's only 1 kcal. So our I2 line should go just below where our I1 line is. Now you may also ask yourself, what about this hump here that shows our activation energy? Should I draw it like this? Should I draw it like this? Well, considering we don't actually have anything that's telling us the rate determining step that has to be computed based on actual reactions, we're just going to draw it as a random size right now. In the future, if you're told that something is the rate determining step, then you do need to know the difference between those peak energies. But for right now, we're just going to say that it doesn't really matter because we're not told what the actual rate determining step is. Now, as a reminder, we can draw from I1 this dotted line here. And this dotted line that we can show pointed downward, this is our delta H of propagation, which was negative 1 kilocalories per mole. Now then, we have our final step, termination. In termination, we're essentially taking this and we're saying we're going down 65 kilocalories per mole in terms of energy. But as a reminder, you have to keep this in mind in comparison also to our reactant energy, right? Notice our reactant energy down here still matters because we have to make sure that we're going to the appropriate side of it. That's where that delta H reaction comes in, because the delta H of reaction is negative 20 kilocalories per mole. So what this is telling us is that the negative of the termination step tells us it's lower in energy than propagation. The negative of the delta H of reaction tells us that it's also lower than the reactant energy. So we can draw that down here as being pretty low on our graph. We'll put it way down here, right? And so now we can once again draw on that hump. It doesn't matter how tall it is. Drop this down and bam, we're at our products. And so we can relate this to multiple different steps, but the most important one is this delta H right here is the delta H of a reaction. That's that negative 20 kilocalories per mole. And as a reminder, that's because we're relating it to that reactant energy, which is where that dotted line came from. We can also relate it to the energy of I2. Notice that we bring that dotted line all the way out here. We can draw this down and say this is our delta H of termination at negative 65 kilocalories per mole. So that's what the energy diagram should look like. Again, it doesn't matter how the tops of the peaks are compared to one another. It just matters where you put the rest of the energies on this diagram. So now that we have this in mind, we can work on this last question. Given the energy diagram, show the transition state for each step. Be sure to indicate partial radicals as well as partial bonds and give their bond lengths, long or short. So the first thing that we want to do before even figuring out the long or short of it, which of course is related to Hammond's postulate, is we want to go through and we actually want to draw the transition states before labeling any bonds as long or short. So let's look at initiation, right? When we talked about initiation, we said that the only thing that's happening is our carbon-bromine bond is being broken. Our bromine-bromine bond is being broken. So what we're going to do is we're going to also draw that out for our initiation, right? All it is we have our bromine, and the bond between them is only partial because it's being broken. We can also draw in some partial radicals, right? As a reminder, anytime we're looking for partial radicals, we're thinking about what has a radical at the beginning or end of a step. And if we take a look at our initiation, both bromines end up with a radical at the end of it. So because of that, we draw them both with partial radicals. So this is most of the important parts of our transition state. Now what we need to do is we need to give our bond lengths as long or short. So let's look at Hammond's postulate and how that relates to this step. Well, looking at this energy diagram, Hammond's postulate states that our transition state is going to look like whatever it is closest in energy to. And this is why it doesn't matter how high that hump is at the moment, because in both cases, what we would say is that if we look at that peak energy for the transition state and we look at what's closest, it's clearly I1. So for our initiation step, it looks like I1. So what is I1 here? Well, we already identified I1. I1 is the two bromine radicals. So that's after the bond is broken. So when we look at this step and we're talking about a long or a short bond, if the bond's broken, that means that this bond in the transition state is going to be long. As a reminder, if this looked more like the reactants, that's when the bond would be formed, and that's when you call it short. Let's do the same thing with propagation 1. Now for propagation 1, we're not going to include the resonance because the resonance doesn't really work in terms of our transition state since that's just always happening. Instead, we only care about the bonds being broken and formed during the actual reaction. So in this case, what we can do is we can say the carbon-hydrogen bond is breaking, the hydrogen-bromine bond is forming. So let's go down here and let's take a look at that. Well, we need to draw our full structure, which has our carbon-hydrogen bond being broken, so that's going to be shown as a partial bond, and our hydrogen-bromine bond is being broken. That's going to be shown as a partial bond. Of course, now we have to worry about where our radicals are. The bromine started out with a radical in this step. The carbon ended up with a radical in this step. This is almost it. Now we got to use Hammond's postulate. So looking at this step, now as a reminder, our I2 is just a little bit lower than I1. So for our transition state here, it's closer in energy to I1 once again. So this should also looks like I1. Well, what does this do for propagation 1? Well, for propagation 1, I1, as we said, is related to these species here. So it's when the hydrogen-bromine bond is not yet formed, it's currently considered broken, and the hydrogen-carbon bond is still formed. So what we can do is we can come down here and say, since that carbon-hydrogen bond is still formed, this must be a short bond. And then the hydrogen-bromine bond must be a long bond because it is not yet formed, it's still considered broken. Now we can do the same thing for termination, right? Looking at termination, we're forming the carbon-bromine bond from the tertiary radical. So let's go ahead and show that in terms of our transition state. In this case, we're going to draw out that exact same structure as beforehand, but we're just showing that carbon-bromine bond as dotted line. Now then, we can also add in our partial radicals because both our carbon and our bromine started out as a radical. Lastly, we need to use Hammond's postulate to determine the short and long of this. So, of course, looking at this one, it's very clear that our transition state is closer to that of I2. So what is I2? Well, I2 in this case would be considered the product of propagation 1 as well as the reactant of termination, right? Because this side would be considered the products. So if it looks more like I2, that's before the bond is formed. Right, so we can say this looks like I2, and so since our bond is not yet formed, it's going to be considered long. All right, and so that's how you get to approach these problems whenever you look at them in terms of the energy diagrams, the actual bond association energies, and then using all that to use Hammond's postulate to determine transition states.